Hey all, and welcome back. This is going to be the first of our lectures on Introduction to Mathematical Models of Infectious Disease. I'm going to be doing a little bit of overview on what mathematicals are, what they do, and then we're going to be talking about compartmental models and how they relate to epidemiology. Again, I've posted some videos and readings. Please check them out. Also, the chapter in Giseki on infectious disease transmission modeling is really helpful. So check that out. Anyway, here we go. So remember, in epidemiology, we have the host, environment, agent triad. And this, basically, when we're talking about infectious disease, this includes all the main sort of components to what allow infectious disease transmission to occur. And one way of quantifying relationships between the epidemiologic triad is using mathematical models. These are models which describe the behavior of how hosts and agents interact within their environments. Why do we do this? We might want to do things like limit the extent of infection through some sort of form of control. Models can allow us to develop strategies of vaccination, quarantining, social distancing measures, culling in animals, contact tracing. Basically, it allows us to set up a framework where we're able to sort of pull the levers on different aspects of the transmission cycle, so that we can see what happens. We can model what happens in the future, for example. Modeling is good because it provides us with sort of a cheap means of observing what might happen in nature without waiting for it to happen. We have to decide on the optimal combination of resources to deal with infectious disease. Models provide us with a handy sort of means of doing that as a tool, right? But importantly, we use models to understand the salient features of infectious dynamics, forecasting or predicting outcomes of diseases in communities, and from changes in demographics, community structures, disease characteristics, and control measures. Again, models allow us to set up a sort of, like you would any type of simulation, where we can pull the levers on different aspects of that and change the outcome of that simulation and see what happens. We can run multiple simulations and change multiple things and see what kind of range of outcomes might occur. I think you're going to see why this is important. So mathematical models are relatively old. They started out in 1760 with Bernoulli. He formulated and solved a model for smallpox in 1760. Using this model, he evaluated the effectiveness of variolation, which we talked about in one of the first sessions. This is way back in 1760. We obviously didn't have computers to do these things. Bernoulli was also famous for developing various probability exercises because he was a gambling man and wanted to sort of estimate, what his chances were of winning particular games of chance. Hamer in 1906 formulated and analyzed a discrete time model in 1906 to understand the recurrence of measles epidemics. Ross developed differential equation models for malaria as a defined host vector disease in 1911, and this led to the second Nobel Prize in medicine. And again, continuing our series of old white guys, Kermack and McKendrick extended on Ross's models and obtained the first epidemic threshold estimates. And if you go back to Ross's model and the Kermack and McKendrick model, I think it's completely fascinating how highly advanced they were in doing these models. Obviously, there were a lot of things that were difficult to observe in nature given the technology at the time, and these models were really quite brilliant in many ways. So, I'll post I think the original Ross paper, and you can check it out. So scientific models, there's all different kinds of scientific models out there. We have a real system, this thing that exists in nature. We can perform experiments and get experimental results and then compare and improve the model. We can make a model that system, perform simulations that sort of relieve us from having to perform experiments or observe what's going on in nature. And construct approximate theories, make theoretical predictions, and compare and improve our theory. But the basic gist of any type of scientific model is that we're trying to replicate what occurs in nature. We're trying to answer specific questions about what occurs in nature. What happens in nature and what causes this thing to happen in nature. Now, George Box, here he is, essentially all models are wrong or some are useful. This is absolutely true. Models have to be taken with a grain of salt. They guide our thinking about things like infectious disease. They don't necessarily give us concrete answers because all models, cannot accurately predict the future, as we know. If we could create models that could 100% predict the future, well, the stock market would be a good place to go with that. But everything is left to chance, and even the results of models and information tend to impact how people react and what they do in the future, which changes the outcome of the models. But that's a whole science fiction issue that we won't get into. Recent trends. Traditionally, models have focused on endemic diseases, childhood diseases, parasitic infections, because of the equilibrium properties of these models could be determined analytically and long-term control. So we want to see, especially with vector-borne disease, what is the equilibrium? What is sort of a long-term, sort of stable pattern of disease, so that we can act upon it. We can figure out what the basic mechanisms are that determine that. Now we have more improved computing power, especially after HIV and the later emerging epidemics, even now with COVID-19. This has moved the field towards modeling dynamics of novel epidemics, so predicting future patterns of incidence and seeking actionable factors that can be used to control disease incidence. So before we were sort of modeling what's going on, like vector-borne disease, checking out what is the sort of seasonal patterns and what are the factors that cause these patterns to exist. And now modeling has moved beyond that to forecasting and trying to predict possible scenarios of the future and seeing if we can do something about it before it happens. Endemic diseases, we increased focus on the increasing focus on seasonal and spatial dynamics. Much more attention paid to rigorous model fitting and parameter estimations. The models are becoming more and more complex, and we're trying to get more and more accurate with our models. Integration of genetics and epidemic modeling. So modeling transmission dynamics within specific populations, within specific types of people, within specific genetic profiles, and that includes the pathogen as well. And finally, ensuring models are relevant to public and veterinary health. Once you start digging in literature, you'll see there's a lot of literature about modeling that isn't necessarily practical. It's more theoretical in nature. It sort of depends on what your priorities are. Are you interested in developing new model methodologies that people can use, or are you interested in producing practical models for epidemiologists to use? And this is, sort of the difference between theoretical math and practical math, and I'm sure you've all encountered this before. So, take-home message here is that modeling is a wide discipline at this point, and we have to sort of look at the practical nature of what those models are, what we want to get out of them, and then proceed. There is nothing to the idea that complex models are superior to simple models. Often simple models present us with useful answers to complex epidemiological problems. Complex models provide specific answers, but they are, generally not generalizable to things. And this is sort of an overall problem with statistics and data. Next, we're going to be talking about compartmental models and extending our discussion of this. So stick around.